Okay, I want to start about some brief clarification about assignment 2, certain things. Okay, okay, in your starter code, you will see, for example, the use of variable arguments. I'm not sure if any one of you used this feature in Java previously. Okay, I saw only one of you. Okay, I just want to make sure you understand that part. It's used quite frequently in the class that I gave to you. First of all, let's go to this particular, this class. Okay, that's the only class. AST nodes. Okay, so this class here represents each node in an abstract syntax tree. Okay, I want you to take a look at this particular constructor. You can see there's a constructor over here. Okay, take a look at that. And then I think for me to better explain it, I better go there. Go to iPad. Okay. And then I will just start a new page and then explain that quickly. Okay. Okay, so that's the constructor you're given. So what you should really pay attention to, in many of the methods or constructor I gave to you in the starter code, you will see ... very often. Okay? It's something you can also refer to some link I gave to you in the assignment number 2. It's quite a useful syntax for the programming language. It's called var args, or variable arguments. For you as an implementer, to implement the body of the methods, you can think about this is as if you say AST node and then array children. It's as if you said that. Okay? So now in your body of implementation, you can simply say, for example, children dot length to see how many children are there. It can be 0 or more. Array can be empty. Or you can say children at a particular index I. Okay? That's about the implementer. What's really interesting is on the client side, the caller for this particular method. Okay? Before I show you some simple example, I want to refer you to the test cases that I gave to you. It's used intensively in the test cases. For example, if you go to the tests package over there, you can see there's a class called basic parser tests, right? You can see lots of them. You should study them carefully. But what I would like to do is refer you to one of them, just for the example. Okay? And I'll do a simplified version, just as a quick illustration. You can see over here, for this particular test, this is one way to actually create a tree. Okay? That one I'll leave you to study. That one's quite easy to understand. Okay? What's really interesting is about this particular way. Okay? You can see this giant expression over here is a single large expression using the constructor I just talked about. And this is the way to build an abstract syntax tree. I find that is most convenient way from the client or from the caller's point of view. Okay? Now, okay, anyway, you will see lots of instances like that. Let's just have a simplified version over here to give you some idea. Let's say this. Let's say I want to build a tree that looks like this. If I have maybe expression E, okay, let me just give you some simplified version. Expression E, under which maybe I want to have maybe turn, and then expression prime, okay? And then follow that, maybe I'll just say factor, and then over here I'll just say A, just for example, right? Let's say there's a tree. How do I represent this particular tree using that notation over there, okay? In total, I need to create basically 1, 2, 3, 4, and 5 nodes in total. But how do I build them, okay? The idea would be you start basically build it on the top-down level. I believe this is going to work. You can think about this is conceptually how you can think of it. Okay, if that makes sense to you. Okay, yes. Let's see. Now let's see how we can do it. First of all, how do I create this? New AST node. And remember, the first argument is always the label. In this case, that'll be E. Okay? E over here, and then followed by 2 children, right? This will be the left, this will be the right. Okay? So let me put this guy first. And then this will just be another tree. So I'll say new AST node, because it's expecting 0 or more, right? AST node. And then this one should have label T. Okay? Should follow a little bit more, but let me just get there in just a moment. And then Oh, actually, let me just finish that, okay? And then follow that, you also have a factor. So this will be new AST note, and then over here, just F. So now this will be terminating because we can have 0 more. Okay, so no more children beyond F, right? No more children. That's external nodes. So far, what we have done, you can see this guy over here. Let me just be more precise. This guy over here is exactly this particular subtree. Okay, good. So far, so good. And let's now go on to do the right subtree. This guy here. So now I'll say comma. Okay, you can think about this is going to be the second argument for this particular root node. This is the first argument. This is second arguments. Right. So now I'm going to do something very similar for completeness. So I'm going to say new AST node, and then I would say E prime, and then followed by, sorry, I'm running out of space. I'll just put it here, right, inline. New AST node, and then it will be just A. Whatever terminal or non-terminal you have, you just put a label, and then after this, you just put like that. Okay, so this is the expression for the tree. Of course, you will see much more sophisticated tree in the test cases, but those trees should be quite familiar to you since we did it in the class as an example. Okay, I want to make sure if this is clear to everybody, right? You will see lots of use cases like this. I don't want you to get stuck just because of this, right? For those of you who might be very new to this notation over here, I would say it's quite a nice feature for the language to learn, right? Because it allows the clients to be very flexible. You can just either you say no more after this, or you can say maybe 2 more, right? So it's really flexible. Okay, any question about this? Just about assignment 2. I would say take a look at assignment 2. I think it's quite a challenging programming exercise for you, especially for top-down parsing. Okay, especially when you try to do the example there, you definitely want to base your implementation based on the top-down parsing algorithm we talk about in class. But there will be some corner cases or special cases you want to watch out for. Okay. Anyway, so I'm going to hold office hour on Friday so you can still talk to me. Otherwise, it will be due next Sunday. Not the coming Sunday, but next Sunday. So you got 2 weeks for that. Okay, that should be enough. Okay. Any concern about assignment 2? Any questions you have for me for today? Okay, I will advise start as early as Mahu. Assignment 1, yes. I will try to get back to you. If not by this Friday, I'll make sure it's available to you during the reading week. Yeah, at least I'll release the marks and then maybe some feedback file you can check, and then you can still talk to me after the reading week. Yes. Yeah. The project, yes. Either this Friday, I'll give you some initial instructions. There'll be maybe different phases I would recommend you do. If not this Friday, definitely early next Monday, for sure. Yeah, I really want you to have enough time to do it. Okay. Good questions. All right, so now let's go back to our lecture. Okay. Basically, whatever we're going to cover until the end of Wednesday is going to be covered in your next quiz, which will be the Wednesday after the reading week, right? But we'll try to see how much we can do. But let's still make sure you are fine with all the topics. Still remember, we are still doing the first kind of parsing, which is top-down. After this, we'll do bottom-up as well. Okay, once we have done with these, we're done with all the parsing, and then we got to go on to the next stage. But let's see. Okay, so now we talk about backtrack-free parsing. Basically, this slide we already went over last time. The reason, the rationale of having a backtrack-free grammar for you to do the parsing is that you want to make sure when you make a choices about choosing derivations. For example, again, let me just very briefly to sketch. Let's say over here, right? We did this briefly last time. Let me do it again, okay? Just make sure. Let's say this is the algorithm you have, and I'm pretty sure you have to familiarize yourself with assignment 2, okay? So now let's say this. Let's say so far, I have built an abstract syntax tree or parse tree like this, and this is now the focus, okay? So now for this particular focus, how do I expand this particular internal nodes? I definitely, according to the grammar I got, either choice number 1, choice number 2, or choice number 3. I got 3 possible choices. If you do not support the idea about look ahead, you have to try one by one. In which case, for example, if you somehow choose this one here to begin with, it might be that you have to build such a big subtree over here and realize it's not the way to go. In which case, you have to go all the way backtrack and try the second choice. That's kind of the way of top-down parsing work with backtracking. So now the idea would be we want to avoid that. We want to say, is it possible when you actually expanding this particular node, I will know exactly, maybe this is the one to choose right away. Maybe. Okay, so that's something we want to discuss. The idea would be you want to have a systematic way to calculate so-called first set. Okay, let me just mention that quickly. What we will see by the end of today, we're going to trace algorithms today. Okay, think about this particular production rule, this particular production rule, and this particular production rule. We want to know for each one of them what's their first set. So first is really like a computation you want to know how to do for your quiz number 3. Okay, and it turns out first set will tell you exactly what the first symbol can be if you apply this particular derivation rule. For example, either multiply or divide or epsilon. Okay, epsilon is a bit tricky, which we will talk about. In this case, if it's divide and you know that your current symbol is simply divide, of course you will choose that one. Okay, you don't have to really just choose the first one just because it appeared first. Okay, that's kind of a very quick sketch. And we're going to do the first set calculation today. And also, there's another thing called follow set. We're going to do that as well. Okay. All right. And the rest of the slides basically just talk about point number 2. I rephrased that a little bit from your slide last week. So now the second point is really the critical thing about look ahead. We want to know what's the consequential first symbol if you apply a particular parser rule. Let's say if you got 3 different alternatives, which one should be chosen? It depends on the second point. Okay, that's really the main extension. Okay, but for your assignment 2, you don't have to do this. That's okay. Right? The example I give to you is going to be relatively small, so you don't have to worry about backtrack-free. Right? Just make sure to get the basic one working. That'll be enough for the purpose. You don't really get bonus mark, but you will get my praise. Hopefully that's inspirational. I'll be very impressed if you do the. You know what? I thought about that, but I thought it might be a little bit too heavy for you guys, right? Yeah. But you know, if you do it, let me know. Then everybody will praise you as well. Yes. All right. All right. Look ahead symbol. That's something we'll see today. Okay. All right. So now what we want to do is we want to see how we can calculate the first set. Okay. We gave you some example last time, but this time we're going to see more algorithmic computation, okay? And then I will give you a little bit tips about how you can calculate that when you're given such computation question in the quiz or in the exam. Okay, so now let's understand what's really the definition informally, okay? Let's say we have a T, which is all the tokens, okay? All the tokens, like a while keyword or for keyword, all the keywords, for example. Let's say, what's the first set? And here, alpha over here, when you calculate first set, alpha can be either a terminal, which is very trivial for first set calculation, or it could be a variable, okay? So now, it's going to be the set of symbol that can appear as a first word if you actually apply this particular derivation, okay? So now, this is the kind of the formal definition. Okay, let's take a look, and then we'll trace some code. Let's say the base case, basically. If the alpha over here is simply just a terminal, easy, just the terminal itself. That was easy. That's basically saying if you apply the terminal as a derivation, what can be the first symbol? Of course, that symbol itself. The variable is going to be a little bit tricky, but let's say conceptually how it looks like. Okay, let me give you this definition here. Take a look. Okay, this is more like a specification, like a declarative way of talking about what you should achieve. But the way to achieve it, we have to use loop. Okay, but let me just talk about it conceptually. Okay, if you look at this particular formula over here, this case. Okay, this guy here. Okay, the green one. Basically, it's saying the following. If in the case where alpha is actually a variable, so I'm talking about the second case. Okay, if that's the case, we're going to the first set for that variable will just be all the words W, such that W will just be some symbols, right? There's no variable anymore, just symbols. And then, how can we collect such words? It's like this. For any string, like a W beta, any string that can be derived from alpha with a number of derivation steps for any string, And then we simply collect the first part, just W, okay, in the set comprehension. That's how you can understand it conceptually. Yes?
When you say W is element of sequence star, does that mean that it can be like multiple words, or does it need to be just like one?
So here it should be just a single word. Just a single word, yeah. Okay, it's collect all the single words together. For example, you can think about the multiply here is a single word, right? And also divide is also a single word. You wouldn't consider multiply followed by divide in this case to be a single word. No. Okay, yeah. Okay, and then what we did last time was we actually gave you the answer for all of them, but now we also have some intuition. You can refer to the lecture last week. But now we're going to see how we can calculate them. Okay, we're going to see some algorithm for doing that. Okay, let's see how we can do that. Okay, now let's go back to the first set. And now we want to compute the first set. Again, that's what we said last time. Let's see the algorithm. Again, I would say when you study the algorithm, always keep this particular formal definition at the top, just to remind yourself what's really the conceptual definition for the first set. And then let's do it. Okay. When you see the algorithm, it's going to be just called the get first. Okay. The first set is going to be some input and output. The input just going to be some grammar. And notice that the first set can be calculated beforehand, prior to you actually take any input sequence. So it will be calculated only once, okay? Because grammar should be stable, so you only calculate it once, okay? And then let's say you give it a grammar, and then you give it some token, all the terminals, and now the output is going to be something like that, okay? Don't be terrified, okay? The output is just going to be a first set. Think about the first set as like a hash map, like a map. You map from variables or tokens, okay, non-terminals or terminals into a set of symbols, basically. Okay, so let's see exactly how we can do it. Okay, of course you got the algorithm over here, but let's see how exactly we can do it. Okay, we're gonna go over quickly, and then before we go over the algorithm on a concrete example, let me just explain to you some critical phrase in the algorithm you want to pay attention to. Okay. Let me switch, and then let's see. And then we'll do example. Let's say this. If you look at the algorithm over here, okay, so now let's go quickly line by line. It's saying that initially we have to initialize the first set for all the terminals. Okay? In that case, the first set should be, actually this one should be the first of alpha, and this one should be the first of A. Okay, I should really augment that. Okay, anyway, so these two are just the initialization, but we'll get to that part in just a moment. Okay, and then you will notice that we are saying that the first is like a map. Okay, and then we say that before we try each iteration, it's going to be the last first. Okay, and then at the end we want to make sure we also update the last first, and then we want to make sure we are going to run the loop as long as the last first can be expanded. So if you read the textbook, it's so-called a fixed point. We just keep doing until we cannot make any further updates, then we stop the loop. Okay? Of course, when you actually implement this, you have to think about maybe a better way to iterate through the production rule. Anyway, and then two things I want to mention, and then we can do example. If you look at the structure over here, so think about we're going to go over every production rule. Like A produces like a sequence, beta 1, beta 2, etc. Okay? We're going to go over every production rule. I'll give you a little bit heuristics about which rule you should really try first in just a moment. And then notice that we got something called right-hand side. Okay? We'll talk about what right-hand side really is in just a moment. So the right-hand side has to do with some extended version of the first set calculation, as we'll see. Okay? But we're going to talk about it. Okay? I want you to draw your attention to two phrases over here. You will see that a lot when we calculate. Number one is, let's say if we got this particular production, A, and then we got beta 1, beta 2, all the way to beta k. Okay, just got k terms. Okay, k can be anything. Let's say that's the current production we want to talk about. Okay, and then you will say that, first of all, if I want to know what's the first of, let me see over here. I want to know what's the first of A. thinking this way. I want to calculate the first of A. Okay? This is how you can think of it. Imagine that eventually you will have the first of beta 1. You might also have the first of beta 2. You may have the first for every one of them. That's also the first of beta k minus 1. For every one of them, eventually you're going to get a set for each one of them, right? That's the definition for first. Here's my question here. If I want to know if I use this particular rule to derive A, to produce A, what should be the first of A? First of beta 1, I agree with you. That's not a problem. So here's my question. Would that be it? Or maybe under some special circumstances, you may have to include possibly the first of beta 2, or maybe even later. Is it possible?
Yes. Yes.
Okay, I heard yes. You want to justify. For example, there might be a case where maybe I should say should be union with the first of beta 2. Why would that be the case?
B1 and B2 both be variables.
Well, not quite. You're saying that if beta 1 happens to be a variable 1 and beta 2 happen to be variable 2, that would not be the reason.
Beta 1 is nullable, because like there is a way to have it not there, so then beta 2
Will take place over there.
would essentially give us the first.
That's exactly right. Okay. So what Ash just said was exactly correct. Let me repeat it. So that's why you have to look at this particular condition over here to say if somehow the epsilon is one of the possible symbols in first of beta 1 or beta I. So what does that mean? For example, let's say beta 2. If somehow I know that maybe epsilon, oh sorry, that's not epsilon. If I know that epsilon is one of the member in the first of beta 2. Oh, sorry, that's not what I meant. Let me do it again. Let me look at basically beta 1 here. Okay. So now if I know that epsilon is a member of the first of beta 1, so that means potentially beta 1 can be null, right? It's one of the possibilities. If that's the case, for example, if I have maybe beta 1 is a variable, let's say what you just said, maybe one of the possibility is to say or epsilon. So that means in the case where this particular production is applied, so that means beta 1 will just be epsilon. In that case, what can be the first symbol for A? It can be whatever symbol that's for beta 2. It's a possibility, right? So the possibility goes on. Basically, the loop that you will see. Okay, I'm gonna, so this is a critical condition you should know. So that's why I said, so it's talk about beta I being nullable. Okay, that's something you want to know. When you study algorithm, so this is a critical phrase to look at. Okay. If it is nullable, of course, you can go ahead to talk about the second one, okay? And then, when you actually exit from the loop, just one more thing to say. I'll make this a little bit bigger for you, okay? So now you can see there is a for loop over here. And now let me clean that a little bit for you to read it more properly. You can see this for loop here. This is the condition to say if this is true, we're going to stay. And then we're going to keep accumulating the first set, right? And then I want you to tell me something here. You can see there is an if statement over here. We're saying that we're only going to go into this guy here if I is equal to k and also epsilon is in the first of beta k, right? So what does it really mean when I actually go into this particular if statements? We'll put it another way.
Epsilon is all that stuff.
Hmm?
Epsilon is like all that stuff that is calculated
No, epsilon was an option, but you literally pull it from that.
Well, let me put a more precise question for you. What does it really mean? When I exit from this particular for loop, and I realize I is simply equal to k, and a hint for you, you want to look at this particular part. Okay, so these are the two. I'll mention an answer for you, but I would say try to struggle with this a little bit as an insight into the algorithm. Yes, of course.
So, like, the way to get there is epsilon is the first of every, like, all the beta i's, but then you're not including it when you get in the right cycle.
Mm-hmm.
But you realize at that point that epsilon, because of every single, like,
Every single iteration.
is
Yeah.
nullable, then you should actually allow epsilon as a potential first element. So you have to add it there at the end.
Yes.
You do that every single one of them.
Yes. Okay, pretty good. Let me draw a little bit picture to help you later on when you study this particular algorithm. Try to link these two connections together. So these two really correspond to the following condition. Okay. Again, we got A produces alpha 1, alpha 2, alpha 3, all the way to alpha k. Let me just write one more. And alpha k minus 1 and alpha k. When I is equal to k, so that means this particular condition is actually true for every I value, including I equals to 1, I equals to 2, all the way to I equals k minus 1. So that means the following. Oh, I shouldn't say alpha, I should say beta, right? Just to be consistent. Okay, let me just change that quickly. Okay, beta 1, beta 2, beta 3, and also beta k minus 1 and beta k, okay? If we got this particular line here, if I is equal to k, so that means epsilon is in the first set of beta 1. And also epsilon is also a member of the first of beta 2, and etc. All the way to epsilon is also a member of the first of beta k minus 1. So that means up to here, what would be the first of A in this particular case? It would be basically the first of beta 1 union the first of beta 2 all the way to beta k. So this is a very important thing to note. I will take questions if you have any. Raymond, you okay? Coco, question. The previous slide, yes. Oh, by the way, I'm not talking about general. I'm just saying in the case where the loop is running to its maximum of iterations. So that's what's happening. Yes, question. I'll take.
Last first is equal to first, but then one says last first is not equal to first. So
Are you talking about this particular line? Okay, so last first, let's see this. I'm basically talking about the last first is first. I might have some issue over here. I'll fix that. Basically, I try to adapt a little bit from the textbook to really show you what a fixed point calculation is. But I'll look into this, yeah, not to waste your time. And then I'll maybe get back to you on this later. But basically, the idea will be abstractly, you're trying to run a loop as long as you can make some addition to the first set. As soon as you cannot make any new addition, you should stop the loop to avoid infinite looping. Okay, good. Okay. Any question about linking when I is equal to k? That's actually true. Yes, I'll make sure that part is carried forward properly. Yes.
So how come if I just set epsilon into the first set, how come we have to keep looking for like solid words if we see epsilon?
Yeah, so it's all about alternative, basically, right? So now you can think about every element over here, every components for this particular production that A can derive into. Beta 1 may have several choices. If one of the choices is epsilon, that means you might choose not to take beta 1, just be epsilon. In that case, the first of A should also include the first of beta 2 when that possibility occurs. Similarly, also for beta 2, let's say if you also got epsilon being one of the possibilities. In that case, not only that you include the first of beta 2, you should also think about if beta 2 is not there, you should also take the first of beta 3, carry forward. Okay, so the case I talk about is the extreme case, when every beta over here until beta k minus 1 is nullable. In that case, the first of A will just be a union of all the first sets over here. Okay, that's the most critical insight into the algorithm, abstractly. Okay, if any questions, we okay? Okay, let's trace something. Okay, let's see. Okay, So now we'll just do this grammar for today, okay? And we'll try maybe some little exercise later, okay? But anyway, let's try that, okay? I may not follow exactly close to the algorithm, but just get an idea, okay? So here I have some advice for you, okay? Given a particular grammar over here, here's the first, you want to choose the rules to process. From the algorithm, it tells you can choose anything. But I would say when you do it by yourself on the paper, you may want to look for those whose right-hand side starts with a terminal. So you can get something into the first step right away. Okay, that's something when I try it, I thought that might be the easiest way for you to think about. Because for this course, if we don't have a chance for you to implement the first and follow set in one of the assignments, then at least you know how to do it on the paper. Let's see. Okay, let's now do the initialization. Okay, that one is quite easy. For every terminal, okay, we're gonna just put it itself. So now number will just be number. Okay, name will just be name. Plus will just be plus, minus, multiply, divide. This, EOF, and epsilon. That one's really easy to fill in right away. Okay, so now we want to see basically initially every variable their first set is simply just empty. So I don't put anything just yet. Okay. How can we figure out exactly to put in? I cheated a little bit, okay? This is the order that we'll end up having to follow, okay? But, you know, you basically follow this particular principle anyway, okay? So we want to find out some rule which will start with some terminal. Which rules start with some terminal on the right-hand side? Factor, right? Well, you can choose factor, you can choose 10 prime. I would say this one here doesn't quite matter. You can choose 10 prime, that's fine. You can also choose expression prime. But the reason I choose factor is that one there, the first symbol is, the first term is just a symbol. So that's why I chose factor. If you perform a different order of choosing the production rule, you should get just the same result. You might just take more iteration to actually expand it. Okay, good, let's just follow this order first to see. Okay, first of all, we choose factor over here, okay? So now, for factor, basically, let's say the first guy here. If I got factor produces this guy here, okay? Let me just write it out separately. Factor produces this, followed by expression, followed by this, okay? It's very similar to what we said before. A produces beta 1, beta 2, and beta 3. Okay, good. So now, is beta 1 nullable? Definitely not. It's a symbol. Okay, so that means there'll be no possibility of this not happening. So that's a trivial case. So now, so the first of beta 1 is simply just equal to basically this particular set. And the first of factor will just be the first of this parenthesis over here would just be parenthesis. Well, of course, in the quiz, you don't have to do this detail. I want to show you for the first time. You will really hope to handle such rule quickly. Okay? Basically, keep going until you hit the wall. What's the wall? A terminal. If you hit something that's nullable, you should really keep going. That's kind of the rule. Okay? I might stop a little bit for a question. Amen. The beta 2? So here we don't really have to consider beta 2 because beta 1 is not nullable. Okay? So now no need to include the first set of expression in the first of factor, right? That's factor 1 we're talking about because this guy here is not nullable. It's kind of block it, right? You basically keep going. Again, you should really try to look at this particular loop. That's really what the loop is saying. You keep going until you hit the wall. You will exit from the loop, right? Okay, okay, that's pretty good. So now you will be convinced for this particular production rule, we know that the first symbol for factor will be left parenthesis, right? If we apply for this guy here, like a factor produces num, what would that be? Num is also a symbol, right? Okay, so far so good, and also name, right? Okay, we're done with the first one. Any question? Okay, so now we can also try another one that will also start with symbol. Let's say we try expression prime, okay, according to my agenda here. If we try expression prime, then now you can also get something very similar, right? It's a symbol, it's a symbol, it's also a symbol. Epsilon is also considered as a symbol, okay? So now for expression prime, we can now put plus, minus, and epsilon. You can see none of these are considered as nullable. Epsilon is the only thing, so as far as the first set is concerned, you can just include epsilon. There's no other variable after that to go over, so you don't have to worry, okay? Everybody's okay? The expression prime is also very easy. Okay, let's go a little bit further. So now the next one would be term prime. Okay, let me use a different color. What about term prime? Term prime is over here. Well, yeah, exactly. Very good. Multiplication, basically the first one, right? Also, they are not nullable. Okay, so now let's try to look at, let's say, t over here. Okay, for t, what we should do is, I'm going to give you some extra example. Okay, let's finish this first. So now let's say for term, t over here. So now this is more interesting. Okay, so now what we want to do now is to have a new page. First of all, I'm going to isolate this particular guy to make sure everybody's okay. Okay, the same grammar. And now we want to do for term. Produces the factor, and then term prime. To begin with, as you will see in the algorithm, the first of term. Initialize that to be just the first of the first variable, just factor. It's always the case, right? So now the question is, should we also include the first of term prime into the first of term? Okay, I heard no. Why is that? So imagine that, think about this. Before we run the very first iteration for the for loop over here, right? Before we run it for the very first iteration, we always initialize the first set for this particular variable we're considering, okay? The first one should always be the first of the first symbol here, which can be a variable or can be a term, like a symbol, like a token, okay? So now the question is, should we actually include term prime's first set and union that into the first of term? That's my question. I heard no. Okay, Raymond, explain.
Because factor is not nullable.
Exactly true. Okay, so now what we want to know is factor here, you can see this is not nullable. There's no epsilon over here. Okay, so now we say because factor is not nullable, so we don't include the first of term prime into the first of term. Okay, good. Any question about this? So far we are pretty, this computation is pretty easy so far. Okay, so now it will only just be the first of factor. Okay, so the first of term will just be the first of factor, which will be this num and also the name. Okay, so far so good. The last one I want to do is expression. What about expression over here? Let's see if we can compute quickly. What about expression over here? You definitely start with the first of term. The first of term we have already calculated, which would be this num and also the name. Now, should we also include the first of expression prime? Yeah, okay, let me make it clear. So now this is the rule that we are talking about. We definitely want to include the first of term, which we did already. Should we also include the first of expression prime? It depends on whether term over here is nullable or not, is it? Not really. Well, of course, you gotta be a little bit more careful if factor itself is nullable, hypothetically. if factor is nullable and term prime is also nullable, and of course term will also be nullable, right? Remember we talked about nullable before, okay? So now in this case, no, okay? So we are fine for now. Okay, that's basically a quick walkthrough about how we can calculate the first sets for everything. But so far, it's not exactly interesting because we always hit the wall right away. Well, or not, or hit the wall either not at all or just after the first term. Let's try something very quickly. Yes, go ahead.
We not use a golden blue table. What's the point of the table?
Oh, the blue table? Oh, actually we did it. We did. Thinking this way, to be more formal. The Mahout's question was like this. Did we actually use a formal blue? We did. Right here. Remember over here for the factor that produces this guy here, right? So now what's the first of parentheses? We got to refer to. I know it's quite straightforward, but it's still defined in blue table, right? Yeah. I would say typically if I ask you to construct, I would say now construct, maybe to save your time, I would say construct the first set for all the variables. For terminals, we know that it's right away, it's a singleton set. But just as a formal definition, you still have to put it.
So when we program, like if I want to program this,
I would say, let's say, if this happened to be in your assignment number 3, if it happened to be, maybe not, maybe. In that case, do you have to store a separate table to map from every terminal to its singleton set? Not necessarily. You can say whenever you try to handle a term, if that term happens to be a symbol, you know that its first set should be just itself. Okay. I'll say it's up to your implementation. We don't have to worry at this level here. Right. I want to talk about just one hypothetical example here. Okay. Let's talk about it. And then we can talk about why first set may not be sufficient. We'll talk about it in just a moment. Let's say the same grammar here. Hypothetically, let's say I got another rule. Simply V, just V. Okay. V produces, for example, let's say turn followed by turn prime followed by expression prime. Don't ask me why, just hypothetical, right? And then followed by factor. Okay? So now I just want to give me an idea. If I want to calculate the first set of V, of course I need to initialize it to be the first of turn over here. That's only example number 1, actually. So now, would that be it? Yeah. That'll be it, right? Because the factor itself is not nullable, so we stop there right away. Okay? Let me change that slightly. Okay? Let's say I don't have that. Okay? So now, what would be the alternative version? What would be the first of V? I definitely want to get the first of term prime, for sure. Right? Agree? Because now not only that one's for sure. I should also include the first of this because term prime is actually nullable. Right? So I should also go union with the first of expression prime. Is that it?
No, sir.
No, because expression prime over here is also nullable. I should say that's also union with the first of factor. You need to remove the epsilon? Yes, of course, yeah. That's something I'll leave to you. I'm just saying conceptually, that's how you do it. Yeah. Okay, any questions about calculating the first set? Removing the epsilon means you will see this. When you actually first, okay, let's be precise. When you say the first of term prime, we know that it's going to be multiply and also divide and also epsilon, first of all, right? If you talk about it. But when you do the union, you will see the algorithm. Okay, I will point to you exactly which point. They said you should put it exactly over here. The first of the current, not here. The first of the current one we are looking at, and then minus the set difference, the epsilon. So you can calculate throughout. Okay. So you don't really you only include the epsilon when necessary in the last step. Okay. So now what you will do is over here, you can think about this guy over here minus epsilon implicitly, of course. And also this guy over here also include the epsilon, remove it from there, and then lastly, you're going to say the first of factor. In that case, it doesn't contain an epsilon. Okay? Everything together, you don't have the epsilon. Okay. Hopefully, everybody got a big idea about how to do this. Okay? I will try to give you some new grammar to think about how to calculate the first sets, maybe next time.
So, just to be clear, we remove term because based on the code, it only takes one that have normal.
Sorry, say it again. I don't quite catch you.
So based on the code, it will only take the variables that are normal.
Yes, that definitely. Yeah, because the reason that we got to include all of them over here, all of these, simply before we take the factor, simply because they are all, both nullable. Okay, so now, again, if when you study the algorithm, this is the condition. As long as epsilon is in the current position, beta I. Okay, thinking this way. A produces something until, let's say, beta I, and also beta I plus 1. If I know that beta I, epsilon is in the first set of beta I know that it's possible this might just be epsilon. In that case, I should also include the first of beta I plus 1 into the first of A. That's basically what we're doing. Okay. Any question about first before we move on? Mahu?
So we can have a case where all the data are like
Nullable? That's definitely possible. In which case, of course, first of all, you go all the way union for all the first set, and then the final one, that's a good question.
do we have the absolute?
You do. That's a very good question. And what you're concerned about is exactly this. Okay, first of all, you can see this particular condition here. First of all, you will see, you will go all the way to I is equal to K. That means you union all the beta 1 up to beta K. Okay, and then since the last term, the last one is also beta K, which is also nullable. Of course, you got to make sure epsilon is there. That's exactly the case you're talking about. All right, any more questions about first calculation? Okay, good. That's good. So now we should talk about what could be, after the first, we talk about some extended version very quickly, okay, and see why it might be useful. Okay, that's the signature for the first set. What we want to do is, one more thing to mention. The way we talk about accumulating from the left all the way to the first hitting the wall, right, for the first non-nullable set, you will see that there's a particular variable here that's really important, which is called the right-hand side. When you study the algorithm, pay attention to how this particular right-hand side is being used. Okay? What it is doing basically is to make sure, let me just illustrate very quickly. Okay? Again, if you have this guy here, A produces beta 1, beta 2, all the way to beta, let's say, K. 2 over here, up to here, if by default, right-hand side will just be the first, I'll say F, the first of beta 1. Okay? Now, if, let's say, epsilon is one element in beta 1, which means beta 1 is nullable. In that case, I must also include the first set accumulatively, right? In that case, right-hand side will just be the same as the right-hand side union with the first of beta 2, and etc. That's what the right-hand side is doing. So in the not really worst case, in the extreme case, maybe right-hand side will be carried forward all the way to union the first of beta 1, the first of beta 2, all the way to the first of beta K, if all the previous beta are simply nullable. Right? So the calculation of right-hand side over here suggests when we calculate the first set, we don't necessarily just have to restrict the argument to be a single variable or a single terminal. It can be just the whole right-hand side. Okay, that's what it's telling us. Okay. Anyway, just pay attention to the right-hand side. Okay. Let me go back to the slides. So now what we want to do is to have another version of first. Okay. I call it overloaded, just like a different argument, right? It's more like a Java term. So now the first, you can see the argument is different. We're saying that it can be either a variable, either a terminal, or some epsilon or whatever EOF end of file. But it can be a sequence of them. Basically, the right-hand side of a production rule. For example, of course, first may also take like a beta 1, beta 2, all the way beta n, right? And the way you calculate this extended version is just how you calculate the right-hand side, as I just explained. Okay? Okay, more precisely, okay, let's try this. So now, this guy here, let me just ask you this. Okay, I'll stop right here, okay? Well, I'm trying to do a set comprehension. Okay, what I want to do is I'll prepare this well for you to think about. Bear with me. 30 seconds. The first of beta 1, beta 2, all the way to beta n. And then first of beta 1 union, okay. Okay, you look at that already, so let's have a look at this. Union all the way to the first of beta k. Imagine that k is maybe somewhere in the middle, somewhere, the index. If I tell you that the first of this particular beta is simply the union of the first k beta, right? First beta 1, beta 2, all the way to beta k. Somehow, starting from beta k plus 1 all the way to beta n, is simply the first set are not included, right? That's a general definition. But what does that really mean? Say it again, sorry. Beta k, yeah. What about beta 1 to beta k minus 1? They're all nullable, right? You see what I mean? Okay, okay, very clear again. Okay, so now the follow. Okay, I think you got it. Just phrase it a bit wrongly. Okay, if I want to calculate the first of this particular sequence, right? Beta 1, beta 2, all the way to beta n, n terms. If it happens that it's only equal to the union of the first of beta 1, beta 2, all the way to beta k, only I'm cutting off right here. So why do I not include the first set of beta k plus 1 all the way to beta n? Why? What could be the reason?
Because it's not ever possible to go to that direction.
So that means I'm hitting the wall right there,
Yeah.
right? Good. So that simply means basically beta 1 is nullable. Beta 2 also is nullable. I just say null, that means nullable, okay? All the way to beta and also k minus 1 is also nullable, right? But beta k is not nullable. Otherwise, you would have included beta k as well, right? Okay. Guys, is that okay for you? Abstractly. Good. So that's why when you see the definition over there, it's exactly saying that. It's saying that all the beta before k is nullable. But k is the first symbol. How about the k is the rightmost symbol in the sequence that's not nullable? Leftmost. Leftmost, exactly. You're listening to what I'm saying. Yes. Beta k is the leftmost symbol in the term that's not nullable. Good. Good. Anyway, just trying to explain the definition to you. Okay. So now let's do a little bit quick example. I don't even need to go to iPad. Okay. But we can go there if we need to. What will be the first of this particular production rule? You can see later on, if you do want to support your top-down parser with the first set calculation, you definitely should really try to overload the version. Okay? Let's say, for example, here, I say the first, I'm talking about this particular rule for expression. Okay? Definitely, you should include the first of term for sure, right? Is term nullable? Everybody following? Okay. You definitely, if you think about this is beta 1, this is beta 2. I definitely should start with first of this particular thing, the whole thing should be the first of terms to start with. Should I include the first of expression prime? I shouldn't, because third is not nullable. Okay? Good. Would be whatever it is. Okay? What about this guy here? Just plus, because plus is itself not nullable, right? That one's easy. Okay? What about the first of minus? Similar? Okay, just minus. Very good. You guys got it. Epsilon? Just epsilon. Okay, good. We'll talk about epsilon in just a moment. That one deserves a little bit of special treatments. We're going to see. Okay, any question about the first set computation? Okay, so what you would be expected to do, maybe in the quiz or the exam, would be I give you a particular grammar, and then either I say calculate the first sets, maybe for all the variables, or maybe I'll choose some particular variable for you to calculate the first set. Okay, good. So we'll talk about first set, and now we want to have a little bit of discussion about the first set. It's really sufficient to ensure we are backtrack free, basically. It turns out it may not be. We might need another help, another set. Now the first, well, second is not exactly symmetrical, it's just a sequential, right? Follow. It's called follow set, basically like a last, okay? No, we'll see, we'll see. Let's understand a little bit about the intuition here, motivation, okay? Let's say we got just a fragment of some grammar. Let's say you got 3 rules, 1, 2, and 3, so we can refer to them. So now, let's say you don't have the look ahead, just a normal parser that you're gonna do for assignment 2. Now we want to expand let's say current focus is expression prime. We want to expand it using either 1 or 2 or 3, okay? And then it would be very nice. You can look ahead to decide which symbol we should get, right? So now a question for you. Of course, you got first will be plus, and the first of minus will be minus, and also epsilon, right? That's something we know pretty well already. Okay, so now, question. When would you choose rule number 3? Conceptually. Hmm? When the word's empty? Not quite. Remember, word is not empty. Think about the context over here. I'll show you some diagram here. What we're talking about is like this scenario here. Let's say currently, this is the tree that's been built so far. Okay, that's a tree. Okay, arbitrarily big. And the current focus is this particular expression prime. Okay, now we can either choose 1 or 2 or 3. Okay, which one should we choose, right? My question, of course, there will also be maybe the current word, right, in the algorithm. Maybe, huh? Okay, you're saying maybe if maybe it can be maybe just multiply, for example. In which case, let's say current one we want to match is multiply. Multiply apparently is not plus, it's not minus. Agree? So now, question for you. Let me make my question very clear. Okay, let's say the current word we want to match, and of course you're gonna struggle with this for assignment 2. Okay, let's say current word is simply let's just say A. Okay, just like a terminal A. Can I say epsilon is simply not equal to A? So I'm going to report a syntax error. That's the question. You may have to go to other branches, right?
Having an epsilon doesn't necessarily mean it's wrong.
Yes. Okay. So that's something you want to be careful when you implement your algorithm for assignment 2. So I think doing your assignment 2 while you study for the next quiz will be very beneficial. Okay. So now, if I simply say A not equal to epsilon, and then I say syntax error, and this is apparently wrong. Okay. Let me just mention that quickly. Okay. In case where A does not really match the plus, A does not match the minus, in that case you must choose epsilon. Okay, and the way you choose epsilon is by as follows. Okay, first of all, conceptually you can think about the tree goes like this. Expression prime is going to have a children just correspond to epsilon. Remember, when you actually get the leaves for your assignment 2, you have to return also the epsilon node. Be careful. Okay, let's say after this, what we should do is switch the focus, right? And that's why I also put a hint over here. You should also remember that when you do assignment 2. the way to handle the epsilon transition is a little bit different from normal transition. You have to say the focus now should be equal to whatever you pop from the stack. Okay, that's something you should keep in mind. And diagrammatically speaking, so that means we're going to basically pop off this particular element here. So that means now the focus will just be over here. So we're going to start from this particular node and try to expand it further. Agree? Any question, first of all? So the pink one over here could be, for example, maybe it's simply maybe just turn. And then in that case, you have to now, after handling the epsilon transition, you have to grow this particular turn structure. Okay? Any question, first of all? This is how you would handle the epsilon transition. Again, you only choose epsilon when the current word does not match plus and does not match minus. You choose that. Okay? So now, question here. Is it possible that when we try to build this particular turn over here, we will still find that it's simply a waste of time or a waste of resource? It's possible, right? It could be that starting from this particular turn, we still build a giant subtree over here and find that it's simply not going to match the current word. And we have to go backtrack all the way back to the turn and decide that, oh, we just made the wrong choice. And we also should go back all the way to the root and find that we just made the wrong choice. There's simply no such word for us to match. In that case, it would just be a syntax error. It's still possible, right?
Can't you just check if it's null?
Hmm?
Can't you just check if it's null?
What is nullable? No, nothing to do with it. Nothing to do. Let me just make my point again, and then we'll see why we can help. We can resolve this issue by introducing another set. Yeah, let me make my point first, and I'll take a question. Okay. So my point is, when after you have handled the epsilon transition, you have switched the focus into this particular term, and then you go ahead and try to build maybe another giant subtree. It's possible eventually you just find out you have to go backtrack all the way to maybe the star symbol and realize that it's simply just not possible to match this particular input token sequence. So eventually you still have to report a syntax error. Wouldn't that be nice if at this point over here or in a situation like this, we can report a syntax error right away if we can decide it's a syntax error? That's kind of the motivation. First of all, we want to avoid backtracking. Coco.
Example specifically for epsilon. But if you have, let's say you have to see, let's say plus term factor prime as well, then you look ahead will see like plus will match it too. You have to.
You still got to go ahead, but I'm just saying, yeah, just for epsilon, yes. So if you actually go ahead for the plus and minus, you might still have to, you just go, yeah, you still have to backtrack. It's still possible. Yeah, that's unavoidable, yes. Okay, so now, well, we will see, huh? Yes.
So expression is actually nullable, right?
Expression where? You mean the,
Expression prime.
it is nullable, yes. Okay, what do you want to say? Yes?
So if you have a character A, how do you go to that nullable branch in the first place?
If you have a nullable over there,
Yeah, so expression prime is nullable, right?
yes.
So
So, it could be that, for example, it could be that when we go, okay, first of all, when we handle this particular epsilon transition, we're going to switch the focus, right, from the top of the stack. And now this would be the new focus. It could be that maybe somehow this term potentially can develop A for you to match. In that case, you're still fine. You see what I mean? Yeah, let me just repeat in case you're not convinced, okay? What she was wondering about. Given that expression prime is nullable, I agree. The way to handle the epsilon transition is by saying whatever that's on the top of the stack, we simply pop it off to be the new focus. That means we can move on to the next internal node to expand without worrying about the current one, because that's simply just epsilon. So now if we simply say current expression prime is simply derived into epsilon, then we can just go ahead to the next one. And now for turn over here, potentially, you might develop something that can match A, so you can just go ahead. Okay, potentially.
yeah, so basically that means the first set of the parent of the expression prime and the term will include the first of both of them. So basically, if you have a character A, that's because that parent first of that parent.
Or we'll put it this way. since expression prime can produce epsilon, okay, whether there will be a match later really depends on what's on top of the stack. Agree? Because if somehow the term has a first symbol that can give you A, in that case, that'll be a good match. If none of them will actually give you a match, then you have to do something else.
Yes, so that's my question. So none of that gives you a match, that you couldn't include a character A in the first set, right? So you have no character A in the first set, why would you?
In the first of which one?
So like, for example, so expression prime doesn't have character A,
Mhm.
so the first set doesn't have.
Well, the thing is, you wouldn't really know what's really on the top of the stack. That's a problem.
I think it's saying why you choose expression prime in the first place.
Why did I'm just making it arbitrary. I just say, let's say somewhere in the middle of building my parse tree, let's say currently it's simply just expression prime. I'm trying to expand. Okay, so now I'm facing a choice. Either I should go for plus, or I should go to minus, or I should go for epsilon. In this case, I will go for epsilon simply because plus doesn't match the current word, which is A. Minus also doesn't match current word A, so I have no choice. And then if I choose epsilon, I may succeed or fail later. I don't know. It depends on exactly how this particular current node is going to help me.
Okay, so my question is, so for example, you have already built the first set of everything, right? You have the first set of everything. For example, if the parent of expression prime and term is A, let's say that's A, so the first of A whoever includes let's say that's B, the capital letter B. For example, the capital letter is B,
Capital letter B in where?
the parent of expression prime and term.
You know, how about this? Let me take your question maybe offline, and then I'll try to summarize it. Maybe that'll be better for everybody. Okay. I'm just worried if you if our conversation confuse everybody. That would not be so nice. Hmm? Okay. How about let's discuss that offline, and then I'll try to summarize that for everybody. No problem. Okay. Good. Anyway, so that kind of motivating scenario, we want to make sure when we actually take the epsilon production, it would be very nice if we can know, since expression prime potentially can just have nothing, can produce nothing. So we want to know what can actually follow expression prime. Thinking this way, in which case, if we know that expression prime is going to be nullable, can be epsilon, whatever variable that might come afterward, okay, we want to know what can follow expression prime. So this is so-called a follow set. Okay. Anyway, so now not only just the first set, we also need to talk about the follow set. Okay, maybe we should discuss after class. Maybe you can make the motivating example maybe even better. Okay. Anyway, okay, let's talk about the follow set. Okay, at least we can talk about how to compute it today, and then we can maybe talk about your example next time as well in the class. Okay, let's talk about it. Okay, exactly what I said. So now what we want to know is given, for the follow set, the number one thing to note, in the case of the first set, the argument there can be a production rule, the right-hand side. It can be a single variable, or it can be a single terminal, right? But for the follow set, in some way, it's easier, in the sense that, so now, the argument can just be a variable. So you only try to calculate the follow set of a particular variable. Okay, let's understand informally what the follow set really means, and then we'll make it formal, and then we'll calculate. Okay, got some time. Okay, so now the follow set of a particular variable v means the set of symbols that can appear to the immediate right of a string derived from alpha. So what do I really mean? Okay, let's take a look at the formal definition quickly. Okay, it's over here. How about I just read this through quickly, and then I will switch to iPad, give you a little bit of understanding. Apparently, we're trying to collect all such word, W. But now, where is W, basically? Okay, let me switch to iPad. Let's try to understand it. So don't worry about the example just yet. We'll get there. Okay. So now, let's see this. So the follow set of a particular variable, okay, it must be variable always. Cannot be a terminal. You don't really calculate the follow set of a terminal. You don't do it. Okay? And then it's going to be all such word W. Okay? Let's now say W, X, and Y. They're all individual words. Okay, 3 different words, string. Okay, you're saying that if somehow V by a number of derivations can go into what am I writing here? So here, go into X. Let me just see over here. Okay, V can somehow produces X, and then I got it. Yes, I got it. Sorry for I was just trying to read it. Okay, we want to know what can follow variable V, right? We want to know. Let's say the following. If V can tell, it can always produce this to some particular string X. Okay, so now I want to know, and this X will be, hey, let me see this. V produces X over here, and then followed by X. If I got a star symbol over here, so star symbol by a number of derivations, we actually got X followed by W followed by Y, first of all, right? And then this particular X, you know what? I think to avoid confusion, not just to you, but also to myself, I better switch the order. Anyway, doesn't matter. Let me put it this way. Okay, let me just finish this, and then I'll take a question. Sorry. Let's say we got a star symbol S. By a number of derivations, we're going to get X followed by W followed by Y. Okay? So now X over here is such that X is derivable from the variable V. Derivable from V. So that means by applying any production rule by any order of derivations, we can actually get X. And then here we want to say what can follow X, that is W. We collect all such W. So this is the abstract definition. But how do we compute it? That's the question, right? Okay, any question about this particular abstract definition?
Why is the start symbol not V?
The star symbol? Oh, star symbol over here is simply telling you by a number of derivations. You just don't know how many. I'm just saying if this particular string over here is derivable from the star symbol, that means it's a valid sequence according to the grammar. And then we are saying that if this particular first part is derivable from the variable you're trying to calculate, and then whatever that can follow X is the W you want to collect. That's a follow set. Make sense to you?
So S starts from the start and V starts from how you pass.
That's correct. That's correct.
So W can be a set.
W here is just a word. No, it's just a word. And then we collect all such words in a set comprehension. Okay? Question?
When you say X is derivable, does that mean that X is directly derivable?
Oh, remember the star over there. We're saying X not necessarily derivable from V, maybe by a number of derivations.
But it just produces X alone, or does it?
Yeah, X will just be it's going to be a number of words over here. I need to be a little bit more careful about the membership. I can think about X is just a single word. Yes, X just a single word.
Okay, so just X alone.
Yes, yes. Question? Why over there is just for completeness to say, because in general you don't necessarily only got W as the ending part, right? You might got some part that follow that, but Y over here is not important. Just for completeness. Y may be empty, may not be empty. Okay, but the most important thing is about W and X for sure. Okay. All right. Any question about the follow set? All right. So now let's go on to the follow set computation. So this is basically what you will see as a solution. Okay. Before we can talk about the intuition next time, but I'll rather go through a little bit computation together with you. Okay. Let's take a look. Before I go over the algorithm together with you, okay, I'm actually going over this. Maybe I'll explain the algorithm in a little bit more detail next time. Okay, but the way we think is kind of similar. Okay? Remember the way we calculate the first set? We basically start with beta 1. If beta 1 is nullable, we also include the first set for beta 2, and etc. Right? And now the way we calculate the follow set is by calculating backwards. We start with beta k. If somehow beta k is nullable, we also want to include beta k by minus 1. Right? Just going the other direction. Okay? Conceptually. And then we're going to see exactly how to do this. Chelsea.
Is the end of file like in these cases, but no state expressions in the follow set for every
Actually, in this case, the base case is very quite limited. Remember, we don't calculate the follow sets for terminals. Right? Question? If beta k is actually somehow not nullable, then yes, we don't really proceed. It will be in a way very similar to how we calculate first, but not exactly, but similar. Okay? So I would suggest that we try to look at maybe just 1 or 2 examples about doing it. Okay? We got less than about 2 or 3 more minutes, but let's see how much we can do. I'll explain the algorithm in detail for sure on Wednesday to make sure we can finish about top-down parsing, hopefully, before the reading week. Now let's see this. Okay? So what would be the way to calculate? I'm not going to talk about algorithm per se so much, but just see how we can do it quickly. Okay? Just 1 or 2. Okay? So now, again, I cheated a little bit. This will be the order we're going to follow. Okay? But what would be the agenda? How can you arrange the agenda for yourself? Okay, here's the heuristics. You want to choose the rules whose left-hand side is actually processed. What do I mean by processed? Especially the follow set for the star symbol is simply the end of file. What does that mean? You know that the star symbol eventually can simply contain a huge tree. And then you can think about at the end of it, what can follow that, it will be the EOF. That's a element that should be in the follow set for the star symbol. Okay? So that's more like a starting case for us. And then that's the only thing we start with. And then for every other variable, we simply say the starting follow set will just be empty. Okay? So now, what you really want to start with, maybe just a star symbol first, because we got something for you to try. Okay? So now, how can we do just maybe 1 or 2 examples to get some idea. So now we want to do, first of all, for Go. Okay? Now let's look at this particular production rule. Okay? If you look at this production rule, we want to know what can follow expression. Nothing? Well, thinking this way. Somehow, expression, I'll just mention this particular one, okay? That'll be it. And then we can cover more details. Thinking this way. Expression over here can be, we know Go can simply produce expression, right? At the same time, Go can be followed by EOF. So that means expression can also be followed by EOF. Agree? Okay? So now, at least we should include EOF over here for expression. So that means every time when you are trying to calculate a particular production rule, over here, let's say this. If you have, let me just summarize this, and then we'll continue on Wednesday. Let me just summarize quickly. If I got A produces, again, beta 1, beta 2, all the way to beta n. Okay? So now I will know that at least the follow set of beta n, I'm talking about the last term, should contain at least the follow set of A, at least. Okay? You can think about I will initialize this to begin with. And then I have to move backwards in this direction to see which one should be included further. And that will be similar to how we think about the first set calculation. Similar. Okay? Let's get this straight first. Yes? Oh, no, we are not looking for follow of A. We are saying we are considering this particular production rule. As we are considering it, we are hoping to update the follow set for every one of them, for every one of the right-hand side. So that's why the calculation for follow set is similar, but not exactly the same. Okay. So let me just clarify this, and then we're done. So Coco's concern was I said that we are really considering this particular production rule. So you might think we are calculating the follow set for A. Not quite. Okay. It's assuming that you already got something for the follow set of A. That's why you chose it. Okay. So now you want at least one thing you can do is follow set for the last term can follow by exactly what A can follow. Right? So that will be just follow of A. To start with that. Okay, I'll stop here, and then on Wednesday we'll continue to finish this. Okay.